Hi, I'm Hamilton, doing it the Kiwi way. Now we're covering off cMOS, XNOR and XOR gates. First we'll do the equation. Q is equal to A XOR B. The truth table, we've got inputs A and B and the output Q. The inputs can be 0, 0, 0, 1, 1, 0, and 1, 1. Q is A XOR B all knotted. So when both inputs are 1, normally A XOR B would be 0. In this case it's 1. And now 0 here and 1 up here. The symbol for XOR, XNOR, sorry. You have output Q, you have two inputs A and B. For the pull down network, QN equals A XOR B. QN is also equal to A and B or A and B with our not sign there and our not sign there. The QP is the exact opposite, or the complement, sorry, which is not A or B ANDed with A or B knotted. So let's draw our resistor network. First we do A not or B is ANDed with A or B knotted. Now we do the AND, which is in series. And then we've got A not B again, so we've got another symbol. Trying to be tidier here. This goes off to ground. So not A or B, not A, ORs are in parallel, B, ANDed, here's the AND bit, A and not B. Now what we need to do is do our pull down network, which is this component here. Which is not A and B ORed with A not B. Got our circles here. So A, not A and B are in series. Not A and B. And over here we've got A and not B. Now we need to draw our knots. Not A is equal to, in cMOS configuration, Oops, we forgot our ground down here. Never forget that. And our not B. Almost there. So B goes in, and we've got not B coming out. And don't forget we've got our answer Q here, or our interim result, sorry, C. No, that's not our interim result, it's actually Q, because we don't have that all knotted. Now let's go and look at our XOR, which is a bit more interesting. We'll draw a symbol used in digital logic. Before I just go up and make sure we've got our not sign there, which we do. And we have our two inputs A and B. And the equation is Q is equal to A exclusive OR B. Truth table, we've got inputs A and B and our output Q, and you should be familiar with this by now. So when both inputs are 1 or a high, the output is a low. If any of the inputs are 1 or a high, as long as they're not both, the output is high, and when both inputs are low or zeros, the output is low. Now, let's do our network diagram. But before we do that, we do Qn equals to A exclusive OR B, all knotted, and that is also equivalent to A, B, or A, B, all knotted. We need to simplify this a bit if we want to use least amount of transistors. And the way we'll do that is follow a simple rule. When you break the line, you change the sign, so it's not A, B, dot there, A, not B. And then we can do that again. We'll break the sign here, so Qn is equal to not A or B knotted, dot there again, A or B, not knotted and knotted. And finally, we can draw this. Not A is equal to A, or B knotted. Ended with A or B, because not B is equal to B. Put some brackets around that. And that uses less transistors than not simplifying it and using this network up here. Now let's do our VDD, and our QP is the complement of this equation. So it's A and B knotted, ORed with A and B knotted. Whoops. That's better. Now let's draw this one. First we've got A and B, in series, A and B is knotted, parallel to not A, B, a little bit messy, but it's okay. A, not B. Not A, B. Now we do our pull down network, which is this equation here. A or B, not B. ANDed. With not A, B. Scroll down a little bit. Looking a bit childish. So A and, well, here we are, sorry, A, not B. Not A or B. And our result Q comes out here. And what we'll do is this is our pull up network. And this is our pull down network. I think that about covers that. And now we'll move on, implement it into Multisim. Here we are in Multisim. What I've done is I've used our previous OR configuration in Multisim that we use to test things out. And what I'll be doing is I've saved it as XNOR OR gates. Also, there's another thing here I want to show you is that we'll be using a new connection called on-page connector. I'll call this one A, for example. And we'll place another one called, place another one called B. On page if I said off page. And then we'll create another one called not B. And finally, we'll create another one called not A. With these, what we'll do is connect them up to our switches, and then we'll be able to use these short lines instead of having long lines here and making our whole diagram messy. So I'll speed things up now, and what we'll do is when we're finished, I'll cover everything off. We'll be doing the Q equals A XOR B. The XNOR will be not implementing, that's a simple one, and you can do that separately yourself. So off we go. Right, I've finished this, and what I'll do is just make a quick note here. This is the exclusive OR. So everyone knows what that is. What we've got here is our two NOT gates, the NOT A's and the NOT B's. Then we've got our logic, and our answer pops out Q here, and it drives our load circuit. We'll run that now. So when both switches are closed, we've got 0 volts and 0, 0 and 0 exclusive OR will equal 0, which we've got here, very, very, very small voltage, and the LED is off. When either switch is open, we apply 5 volts and the LED is on. When both switches are open, the LED should be off. We've got 5 volts. 1 exclusive OR 1 is always 0, and this works correctly. You may have noticed before I put my two nMOSs here around the wrong way, and I had my source up here and the drain down here, and this caused a few problems. And also what I did is I gave it a separate VDD for the second switch as well. But that's all been resolved. So now we'll go and implement it on our actual breadboard. So now we've implemented this on our breadboard. I'll quickly open it up. Here it is here. We've got our NOT A here. We've got our NOT B down here. We've got our pull-up network here of only pMOSs. We've got a pull-up network here of pMOSs, pull-down network here of nMOSs, and our answer comes out here, Q. Both buttons are up, so we're applying 5 volts. 1 and 1 equals 0, the LED is off. 1 and 0, I'll start again. 1 and 1 equals 0. 0 and 1 equals 1. 1 and 0 equals 1. 0 and 0 equals 0. Our white wires here are our B signals. The brown wires here are our A signals. The knots, I've kept them all as yellow. Intermediary signals are blue here. And our answer comes out as orange here and drives our load circuit. Thank you very much.